try to share the screen first. Can you see the screen?
Yes, we are seeing screen.
Okay. Okay, thank you very much. So so today my talk is on this glimpse of enumerative geometry. So I'm a newcomer of iTHEMS who joined this in the past July, in the middle of July. So my interest is to study Yang-Mills theory and enumerative geometry on Calabi-Yau fourfolds. So let me start my talk. So so enumerative geometry is mainly about an enumeration. So this means we are doing counting. So counting is one of the first several things we learn in our infancy. So everyone learns first to count things, then we learn more complicated things. So enumerative geometry is a subject concerning the counting geometric objects. These geometric objects can be defined from some discrete data or from some algebra or sometimes from some differential calculus. So let me give you a first example of the simplest example of enumerative geometry. So we are considering just counting the number of lines passing through two distinct points in R2. So this is a two-dimensional Euclidean space. So everyone knows the answer. This is 1, because in this plan, you consider line passing through any two different points. So there's only one such lines. So then we should ask ourselves, okay, how actually we do this count? So actually, I think most people answer these questions because they already know the answer. So you say that, okay, just 1 because I learned it. But in fact, we want to understand how we do this. So the answer is that we first form the space of objects we want. So the space of objects now is just a line passing through these 2 points. So because there's only one such line, so the space of objects is just a 1 point. So if we are lucky, so we get this 0-dimensional space, which is finite, then we can just count the number of the points in this finite set. So here, this finiteness, you see that already compactness of this, the notion of compactness in topology already appears in here because we need some finiteness to count. So then the question is that is this enough? Sorry. So is this enough? So let's consider the second example. So we're considering the number of intersection points of a line and a circle in R2. So now this is a circle, this is a line. So we are asked about this intersection point, to count intersection points. So the most naive answer you get is okay, 2 points, because you see, okay, here is a point, here is a point, so you get 2. But in fact, the answer is 0, so you get 0 points. So why? Because from humans' intuition, we often require the counting to be stable under perturbation of geometric objects. So this means that here we want to deform these two geometric objects, this circle and this line, and we deform their relative position to the general position such that they are destroying. Then because the number of intersection points is empty, so this count is 0. So then from this example, so what we have learned. So the first thing is that we learned is that we need to introduce a notion of orientation, so-called orientations. So this means that so let's orient this circle. So like this. You can also orient in another direction anyway. So you see that the behavior of these two intersection points is quite different. So the orientation here, so it's in this direction and this in that direction. So this means that we should count these 2 points in a different way. So we should we should give different signs to these 2 points. So now 1 plus 1 plus minus 1 equal to 0. So we get this 0, which is consistent with this empty intersection points here. So in particular, working with a complex number is often better than a real number because in a complex world, we have natural orientations given by complex structures on C. So the second thing we learn is that we need to take care of the singularity of our space. Because if you look back this picture, so in here, if this line is tangential to the circle, so we have some intersection points here, which sounds like we should count the intersection point as 1. But in fact, analyzing these intersection points in another way, it gives different answer. So let me first fix this the relative position here. So let's say this is a 0, 0 point, this is 0, 1 point, and the radius of this circle is 1. Then in the equation, the intersection of these 2 geometric objects is the intersection of this circle and these lines. So let's say for simplicity in C2, not in R2. Then the way we do intersection is in algebraic geometry, we consider the ideal generated by these 2 things. And we consider the quotient of this polynomial ring by this ideal. Then you can see that in the end, we get a 2-dimensional vector space. So in a way that we should count this intersection point as a 2 instead of 1. So to sum up, the way we do this enumerative geometry is first we form the space of objects we are interested in. Then we should compactify this to ensure that we have finite number of things to count. And then we orient the space to ensure that we have a nice deformation invariant property. And then we define this counting by perturbation of this perturbation of this space, or analyzing the singularity of the space, just like in the picture here. This is about this perturbation, and this is about analyzing the singularity. So in the end, all the ways gives the same answer. So let me give a first non-trivial example. So we consider the so-called partition. So partition is is about this how to decompose a positive natural number into the sum of several positive integers. For example, we can write 4 equals to 4, or 3 plus 1, or 2 plus 2, or 2 plus 1 plus 1, or 1 plus 1 plus 1 plus 1. So in a way that we have 5 distinct ways to decompose 4 into the plus summation of positive integers. So in this way, we call this we say that the number of partitions of size 4 is 5. So in general, we denote this Pn to be the number of partitions of a positive integer n. Then there's a famous formula called the Euler formula, which gives the generating series of this counting partitions, where the right-hand side is a product formula over all positive I. So the way we read off this so the way we read off this Pn is by gradually expand this this right-hand side and then consider this expansion. So for example, the first several terms is like this. So 1 plus q plus 2q squared, 3q cube, 5q fourth power, and so on. For example, you can see that if you want to read off the number of partitions for this number 4, so we just put this power n to be 4. Then you see that we get 5 here, which is exactly the 5 here. Okay, but more generally, you can consider any n. So we can read off from this formula. So from this formula, what we learn is that writing in terms of transition series makes the formula compact and beautiful. For example, it's very difficult to write down an explicit formula for what is Pm, but the write it in the terms of transition series is quite compact and nice. So this is a remarkable features in the modern enumerative geometry, because this is mimicking the partition function in path integral in this quantum field theory. We consider all possible paths between these two points. So the second example is more complicated. It's coming from this edge geometry. So we consider this complex projective space of 4 dimensions, and we consider a subspace here, which is cut out by this homogeneous polynomial. So you see that we cut out by one equation. So this is 4-dimensional things. So this is a 3-dimensional things. So in fact, this is a so-called is an example of a Calabi-Yau threefold. So this threefold means that this is a complex 3-dimension. So this is a real 6-dimension. So this is called quintic because the power is 5. So a word about this Calabi-Yau space is that so this space is has very nice physical interpretation. It says that this gives example of a space which has gravity, but there's no mass inside this space. So so we can consider this counting of a degree D rational curves in X. So rational curve is basically a sphere in X. So then you can see this list. So when this degree becomes large and this numbers becomes very, very big and quite complicated. It's very hard to guess what is the how can you predict these terms for higher D. But this amazing duality called T duality in string theory. So in mathematics, this is called mirror symmetry, which you can read off all this counting from the so-called mirror Calabi-Yau threefolds. Okay. So the last example is on 4 manifolds. So let's start with a closed-oriented 4 manifolds, real 4-dimension, and let's start with E is SU2 bundle on X. Then we can define the Hodge star operator, which decompose this space of bundle value 2 forms into this plus part and the minus part based on the eigenvalue of this star operator. Then we can mention what is the so-called anti-self-dual connection. So this is a unitary connection such that the self-dual part of the curvature is 0. Then we can consider the moduli space of ASD connection. So that means we quotient out the equivalence relation by the gauge transformation. Then we can compactify the space, orientate the space, and count the space. So this is the famous Donaldson invariance, so which is quite important in smooth topology of 4 manifolds. So so in particular, Witten realized this Gentian series of this Donaldson invariance as the partition function of certain n equals 2 supersymmetric Yamil theory. So anyway, so Witten gave a path integral interpretation of such a invariance. So this is also an example which I said this enumerative geometry has a link with quantum field theory. So actually, my research is to extend the Donaldson theory to Calabi-Yau fourfolds. So Donaldson theory is defined on real 4 manifolds. So we can consider the so-called complex-oriented fourfolds, which is Calabi-Yau fourfolds. So this will generalize the previous example 1 to 3, and in particular, it has applications to curve counting and the so-called 4D partitions. Okay. Yeah, I think my screen is okay. Okay, that's so if you have more interested in what I did, so we can just have more discussions on this part later. Okay, this is the end of my talk. Thank you very much.
Okay, thank you very much, Yalong, for very pedagogical yet very insightful talk. Thank you very much.
Yeah.
So, any questions? If you have a question, unmute yourself and go ahead or raise your hand. Then let me start asking that. So you put 3 examples, very
Yes.
Just for your work, maybe a component of them. But is there any interrelation between those examples, like example 1 and example 2, or it's a different component?
It's quite different. So as I said, this for example, geometric objects sometimes can be defined by discrete data, and so for example, these partitions or solid partitions or plane partitions. So these are discrete data. This is just given in a discrete way. So another way to give geometry is we consider given by algebra.
Mm.
So this polynomials, we can consider variety cut out by several polynomials. So my second example is more about this geometry related to this algebra. So my last example is about this geometry defined by differential equations, because this anti-self-dual equation is differential equations. So in a way that these 3 objects are quite, the nature are quite different. So so how to say? So sometimes they have deep relations, yeah, but depends on the specific context.
Oh, okay. Then let me ask a further question. So you mentioned some relations which objects that attract some interest from physics. So yes. Can you share your view on the relation between physics and mathematics you are involved?
The view of physics, how to say? So for example, I think just previously, people working in this string theory, superstring theory, I think they are mainly interested in Calabi-Yau freeform. Yeah, they consider, for example, they consider the so-called topological string partition functions on Calabi-Yau freeforms. So this has very nice property. For example, it has some relation with the so-called Kopakuma-Wava invariance, so BPS invariance. And also it has some nice property. One, this Calabi-Yau freeform, for example, is a resolved coniform, just very some toric Calabi-Yau freeform. Then you have so-called geometric engineering, relating this topological partition function with the equivalent Donaldson theory on R4. So I think this all these things have some backgrounds in string theory, but it seems that there's not much studies on string theory and all these things on Calabi-Yau fourfolds. So what I study, I think potentially may just indicate some hidden physics which has not been discovered before, because the special geometry of Calabi-Yau fourfolds has just only recently been developed. Yeah. So I hope that physicists can discuss with us, and we can say something more about both sides, basically. Yeah.
Okay, sure, we will. And also explaining to the physicists the way you just gave the talk, that's very pedagogical, and just try to just focus on the principle and actual real content. Thank you very much for the talk. And I see that now Hatsuda-san are raising a hand, so go ahead, Hatsuda-san.
Yeah, I'm curious about this whose formula, Euler's formula, the partition
yes,
of this integer.
Euler's formula.
Euler's
yes.
formula. I mean, did he find the formula by inspection, or how did he find it? And also, what is the meaning of this Q in this case? Because in quantum theory, I mean, for example, its expansion, so maybe it's a loop or H bar or something like this, but is there some sort of meaning of Q in this generating function?
Yeah, that's a very interesting question. So first of all, for the first question, how Ola find this formula. So this is I have to track the history maybe. Yeah, but how to say? Yeah. Yeah, I think I cannot say at this point.
Okay. Yeah. We'll find. Yes.
But for the second questions, I think this is related to people can understand this Q parameter as some for example, if you consider, I think this is related to so-called Vafa-Witten theory. So if you consider this n equals 4 supersymmetry Yang-Mills theory, you can consider the partition function. And in 1994, so Vafa and Witten wrote a paper called the strong coupling test of S-duality. They want to use this the topological twist they construct, now they call the Vafa-Witten twist, to test the so-called S-duality. So in a way that the partition function they consider is essentially the Euler characteristic of moduli space of sheaf on surfaces or general form manifolds. So then they consider the Euler characteristic and form the Jenkins series. So this is a modular form basically. So this is quite related to the partition function here. Yeah, because all those modular form is some power of the function I wrote here. So you can understand that Q as the parameter which you keep track of the instanton numbers for the instant gauge theory. Yeah, this is the formal parameter which label the instanton number. Yeah, for this Vafa-Witten theory. Yeah, for example, if you suitably just do some you have this group SL2Z, you can just under this group action, this Q can becomes other how to say, for example, 1 over Q or minus Q. Then this function, this partition, this function has some invariant property under these transformations. Yeah.
Okay.
Yeah.
Okay. Thank you.
Okay. Any other questions? Hey, if not, maybe you can ask questions in the breakout room, which I will designate Yalong to the speakers breakout room.
Yeah,
Then
let's only myself.
Let's thank the Yalong again